Hello there, and welcome. Tonight, we're stepping beneath the surface of reality into a world where particles blink in and out of existence, and cause and effect begin to blur. Quantum physics isn't just for chalkboards and cold labs. It's the hidden scaffolding of everything you've ever touched, seen, or dreamed. We'll explore a universe where atoms can be in two places at once, where matter listens when it's watched, and where the future might ripple backwards into the past. Not theory, but observation. Not science fiction, but strange fact. And somehow, despite its mystery, quantum physics quietly runs beneath your every breath, shaping the very fabric of the now. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or press the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. In the beginning, there was certainty. An apple fell, a planet turned, and a pendulum swung in clean, calculable arcs. For centuries, the universe seemed to unfold like a giant clock, its gears clicking with predictable precision. Newton's laws, firm and elegant, stitched space and time into a comfortable tapestry. If you knew where something was and how fast it was going, you could tell where it would be tomorrow or 1,000 years from now. The cosmos was knowable, stable, smooth. And then, cracks appeared. At first, they were small, odd flickers in experiments, little contradictions. A beam of light split in strange ways. Electrons behaved more like ghosts than marbles. The rules that governed the falling of apples didn't seem to apply to the tiniest grains of reality. Scientists began to peer into the atomic and subatomic world with sharper tools, expecting more precision, more clarity. What they found instead was something else entirely. At the smallest scales, certainty vanished. Particles flickered into and out of being. A photon might act like a particle in one experiment and like a wave in another, as though it hadn't made up its mind. Electrons didn't orbit atoms like planets around a star. They blurred into clouds of possibility, hovering in ghostly regions where they might be, but weren't quite yet. It wasn't just that we didn't know where things were. It was that the idea of where started to lose its meaning. This was the birth of quantum physics. Quantum, from the Latin quantus, meaning how much. In this new world, nature didn't flow in. Smooth, continuous lines. It leapt. Discrete packets of energy quanta jumped and vanished, like light skipping across water. The solid world was no longer solid. Energy came in bursts. Events happened in jolts, not gradients. One of the first to see it clearly was Max Planck. In 1900, he was studying blackbody radiation, how objects glow with heat. Classical physics predicted that hotter objects should emit infinite energy at short wavelengths, a result known as the ultraviolet catastrophe. But that didn't match reality. To fix the math, Planck introduced an idea almost reluctantly. What if energy could only be exchanged in fixed amounts, like coins instead of fluid? That small adjustment cracked open the door. A few years later, Einstein stepped through it. He used Planck's idea to explain the photoelectric effect, the way light could knock electrons out of metal. But to do it, he had to treat light itself as made of particles. Photons. Light, which had long been known to behave like a wave, now had a particle side too. The duality was unsettling. How could something be both a wave and a particle? But the stranger thing was, it worked. As more physicists entered the quantum realm, Bohr, Schrödinger, Heisenberg, Dirac, they found that the more they observed, the less they understood in classical terms. The atom was no longer a tidy nucleus with neat planetary orbits. Instead, electrons existed in fuzzy regions, their positions a matter of probability. The best you could do was calculate the odds of finding one in a certain spot at a certain time. Reality became statistical. Determinism gave way to possibility. This didn't mean chaos. It meant precision of a different kind. Equations still governed behavior, but those equations didn't tell you what would happen, only what might. The universe, it turned out, was not a clock. It was a casino. And yet, the odds were rigged in favor of pattern and beauty. Quantum theory didn't just describe the world, it predicted it with uncanny accuracy. It explained the structure of atoms, the behavior of semiconductors, the glow of stars, the mechanics of lasers. It gave us transistors, MRI machines, LED lights, and the very screens we watch at night. It's in every computer, every smartphone, every network that connects the world. The modern age is built on quantum foundations, and yet, the deeper you go, the stranger it becomes. Take the concept of superposition. A particle can exist in multiple states at once, or entanglement. Two particles can become so linked that changing one instantly affects the other, even if they're light years apart. Or tunneling, where a particle passes through a barrier as if it were never there. These aren't just theories. They're measured, tested, observed, and yet they defy intuition. They make nonsense of the tidy rules we thought we understood. Perhaps the most unsettling idea is this, that at the smallest scale, reality is not fixed until it is measured. Until then, it exists only as a range of probabilities. The act of observation itself changes the outcome. In other words, consciousness attention seems to matter, not in a mystical way, but in a deeply physical one, as if reality holds its breath until you look. This broke something in classical physics. It broke the illusion that we could stand outside the world and simply watch it. It reminded us that we are participants in the universe, not just bystanders, that we are entangled with it, down to our atoms and quarks. Small does not mean simple. At the quantum level, a single particle carries layers of possibility, unpredictability, and elegance. There are symmetries we barely understand, particles that flip into their opposites, fields that fill all of space, even when nothing appears to be there, vacuums that aren't empty, forces that pop in and out of the void. The deeper we look, the more we see a world humming with subtlety. Quantum physics isn't just a theory, it's a language that reality whispers beneath everything we know. It is delicate, poetic, deeply mathematical, and oddly emotional. It says, "The universe is not cold and fixed, it is warm with potential." Classical physics gave us the tools to build bridges and engines. Quantum physics gave us the tools to build worlds we cannot see yet depend on every day. It is not here to replace the old way of seeing. It's here to complete it. And so we begin. One foot in the familiar, one in the unknown. A journey through 100 quiet revelations. Each one small, but not simple. Each one a doorway to wonder. In a quiet lab over 2 centuries ago, Thomas Young performed a simple experiment. He took a beam of light and passed it through 2 narrow slits, side by side, cut into a sheet. He expected perhaps to see 2 bright spots on the wall behind. But what appeared instead was a series of bands, bright and dark, like ripples in a pond. An interference pattern, something only waves could produce. It was as if the light had passed through both slits at once, overlapping with itself, crest meeting trough in a delicate dance of brightness and shadow. At the time, this wasn't strange. Light was widely accepted to be a wave, like sound or water. It curved, bent, and spread. It interfered. The pattern on the wall seemed to confirm it. Light had no mass, no substance. It wasn't a thing but a rhythm, a shimmering tremor across the fabric of space. But centuries later, as quantum theory took shape, that certainty began to fade. Einstein, trying to explain the photoelectric effect, proposed something daring. Light came in particles, discrete packets of energy called photons. These photons could knock electrons free from metal surfaces, not in gentle waves, but in sharp collisions, like pebbles hitting a window pane. The energy transferred was precise, not smeared. It behaved not like a ripple, but like a bullet. So which? Was it a wave or a particle? The answer, unsettling and beautiful, is both. Light, it turns out, doesn't choose one nature over the other. It possesses both, simultaneously. In some experiments, it acts like a wave spreading, interfering, weaving complex patterns. In others, it acts like a particle striking one point, transferring energy in a single burst. This duality lies at the heart of quantum physics, not just for light, but for all matter. Even electrons, long thought to be tiny balls of charge, show this strange behavior. When a single electron is fired at a double slit, it doesn't go through one slit or the other like a marble. If no one is watching, it behaves like a wave, interfering with itself, creating a pattern over time that only waves can make. Each electron lands in a single spot, but the collective pattern formed by thousands of electrons ripples out like water. It's as if each particle carries a hidden map, a set of probabilities showing all the places it could be, all the paths it might take. And until something observes it, measures it, or disturbs it, that map remains open. The electron doesn't just take one route, it explores them all. Then comes the twist. If we try to watch, if we place detectors at the slits to see which path the electron takes, the pattern changes. The interference vanishes. The electron seems to pick a slit, as if suddenly aware it's being followed. It no longer acts like a wave. It collapses into a particle. Observation rewrites the outcome. The act of measuring breaks the illusion. The possibilities fade, and only one remains. The moment we look, the mystery shrinks. This is not just true for light or electrons, but for all particles, all matter. Everything, at its most fundamental level, exists in this wavering state of both, and until it is seen, the double-slit experiment has been repeated countless times with photons, electrons, even molecules, always the same: waves when unobserved, particles when watched. The boundary between possibility and reality is thin, and it's pierced by attention. This is not metaphor. It's been tested, verified, peer-reviewed. Devices have been built that turn the act of observation into a choice made after the particle has passed through the slits. And still, somehow, the outcome bends to whether or not it was measured. It suggests that reality, at this level, does not exist independently of interaction. The wave of possibilities collapses into a particle of fact only when touched by awareness or its mechanical equivalent. This doesn't mean the universe is conscious, but it does mean it is reactive, that it waits, suspended in potential, until something nudges it into becoming. Light is not just something that moves. It is something that might move in 1,000 different directions until a path is chosen by circumstance, measurement, or choice. You might wonder how something can be a wave and a particle at the same time. But perhaps that question is shaped too much by our senses. We're creatures of middle size, used to billiard balls and gusts of wind. But the quantum world is not built on our scale. In its domain, categories bend. What seems contradictory may be complete. The wave is not just a shape. It is a spread of possibilities, a canvas of where the particle could go, where it might appear, how it might behave. The particle is what happens when that possibility solidifies, when the cloud of maybe becomes a single point of here. Both are needed. One whispers of potential. The other marks a moment of becoming. And this duality isn't locked away in labs. It's happening all the time, everywhere. In the light from distant stars, spreading across the cosmos, in the electrons flowing through your nerves, firing thoughts into being, in the sensors of your phone, converting photons into pixels. Reality, as we live it, is built on this quiet contradiction, a foundation that flickers between the wave and the point, between possibility and presence. So the next time you see a ray of sunlight stretch across the floor, remember, it is both a ripple and a pulse, both a whisper and a knock. A particle of light may have taken every possible path to reach you, weaving a tapestry of probabilities that collapse the instant it met your eye. Wave, particle, both, always both. It begins with a question so simple, it almost feels like a trick. Does the universe behave differently when we're not looking? The answer, unsettling and quietly astonishing, is yes. In the world of quantum mechanics, observation is not passive. It's not a pair of eyes at the edge of the scene. It's an active participant, a subtle force that changes what it touches. And at the smallest scales of reality, where particles dance between states and probabilities blur into one another, simply watching is enough to shape the outcome. You've seen this story start before in the strange results of the double-slit experiment. A single particle, be it light or matter, passes through two openings. If left alone, it behaves like a wave, exploring both paths at once, interfering with itself, and creating a pattern of light and shadow. But if you try to find out which slit it actually passed through, if you place a detector to watch it chooses, the wave vanishes, the interference disappears, the particle behaves like a particle. The act of observing changes the very thing you hope to observe. It's not that we bumped it with our measuring device, or disrupted it with some clumsy tool. The effect holds even when the watching is gentle, so gentle that nothing seems to touch the particle at all. It's as if the particle knew it was being watched, as if awareness itself cast a shadow across the possibilities. This is the observer effect. At the quantum level, it tells us that a particle's properties don't exist in a fixed state until they're measured. Position, momentum, spin. They live in a cloud of potential, described not by exact numbers, but by probabilities. When we observe them, those clouds collapse. The act of measurement doesn't just reveal reality, it creates it. You might imagine a marble hidden under a cup. You lift the cup, and there it is, unchanged by your glance. But quantum physics doesn't work like that. In this world, lifting the cup decides where the marble was. Before you looked, the marble wasn't simply waiting. It was everywhere it could be, and nowhere at all. Your observation didn't discover the truth. It finalized it. This isn't philosophical sleight of hand. It's been demonstrated in laboratories countless times. Quantum particles, photons, electrons, atoms exist in states of superposition until observed. Their wave functions, equations that describe all possible outcomes, collapse into a single value the moment a measurement occurs. The system chooses, or rather is forced to, choose when it is touched by an act of detection. Even more startling are the experiments that delay the observation. In a variation called the delayed choice experiment, physicists have shown that a particle's behavior in the past can be influenced by decisions made in the present. Whether it acted like a wave or a particle seems to depend not on what happened, but on what we later choose to know. That's where the lines blur. Not just between particle and wave, but between cause and effect, between future and past, between what is and what might have been. In this strange quantum landscape, it is no longer safe to say that the universe unfolds independent of our awareness. Our knowledge, or even our potential for knowledge, changes the story. It's tempting to think of this as proof of consciousness affecting the world, but in quantum mechanics, the observer need not be conscious. A camera will do, a sensor, a photon counter. What matters is that the system is no longer isolated, that it is no longer purely in superposition, The instant it becomes entangled with something that can record or reveal information, its uncertainty collapses. The wave of potential becomes a point of fact. Still, the implications linger. The universe does not passively evolve, waiting to be viewed. It coalesces into reality when we interact with it. That interaction, whether by eye, machine, or equation, draws the line between what was possible and what now is. And what does that mean for us? It means that reality, at its deepest level, is participatory. That what we know, what we choose to ask, defines the answers we are given. It means that knowledge is not just power, but influence. That the boundary between truth and discovery is thinner than we thought. It's easy to overlook, living in the scale of tables and trees and ticking clocks. The classical world is robust. A chair remains a chair, whether we see it or not. The moon does not vanish when we close our purses, eyes. But the quantum world hums beneath it, subtle and shimmering, obeying different rules. In that place, reality is not laid down like tracks ahead of a train. It is formed at the moment of contact. The observer effect doesn't mean we control the universe, but it does mean we are never fully separate from it. That by asking, by watching, by measuring, we are always part of the equation. A quiet participant in the unfolding of what is. So much of what we call real is filtered through observation, through what we choose to notice and what we let pass unseen. And perhaps that's the gentlest echo of the quantum truth, that in every moment we are not only receiving the world, but shaping it, not with force, but with attention. And sometimes, just looking is enough to make something real. Imagine a coin spinning in the air, not just flipping from heads to tails, but hovering in a strange in-between where both possibilities are held at once. Neither true, neither false. Just suspended, a whisper of both outcomes, existing side by side, layered, unresolved. Now, shrink that moment down to the size of an atom and stretch it across the whole fabric of reality. That's where quantum superposition begins. At the heart of quantum mechanics lies an idea so quiet, so counterintuitive, that it slips past understanding and straight into wonder. A particle, a single electron, photon, atom, does not exist in one defined state until it's measured. Instead, it occupies all the states available to it. It can be here and there, spinning one way and the other, existing in multiple configurations simultaneously, not as a metaphor, as a mathematical truth. This is superposition, a particle's wave function. The mathematical object that describes its state holds within it every possibility, like a musical chord instead of a single note. It is not until we listen, until we measure, that the wave collapses into a solitary tone. But until then, it is a song of maybes, unfolding in silence. Superposition isn't just a theoretical curiosity. It's been demonstrated over and over again, in controlled environments, in particle labs, and cold vacuum chambers. In one famous experiment, a molecule far larger than a single atom was placed into a superposition, existing in two different places at once. Not metaphorically, not symbolically, measurably. It traveled two paths simultaneously, then interfered with itself like a wave. And all of this from something made of hundreds of atoms, something that should feel too large, too solid to blur. But in the quantum world, size is not the limit. Isolation is. The more isolated a system, the more it resists the pull of classical certainty. Left untouched, unobserved, unmeasured, a quantum object retains its fluidity. It holds open every door, but the moment it interacts with the environment, even a trace of air, a whisper of heat, a photon of light, its superposition collapses. It becomes something singular. One path, one answer, one result. This collapse is where mystery begins. To illustrate it, Schrödinger imagined a cat, a thought experiment, macabre and surreal. He asked, "What if we placed a cat in a sealed box, alongside a radioactive atom, a detector, a vial of poison, and a trigger? If the atom decays, the detector registers it, the poison is released, and the cat dies. If it doesn't decay, the cat lives." But quantum physics says the atom is in a superposition, both decayed and undecayed, until it's observed. So what about the cat? Inside the box, sealed off from the world, it too enters a superposition, both dead and alive. Both possibilities, real and unreal, coexisting in a strange quantum state. Not because the cat is quantum, but because the decay that seals its fate is. Until the box is opened and someone looks, the cat's state remains unresolved. It's not a trick or a riddle. It's a challenge to our idea of reality itself. Of course, in practice, cats are not quantum objects. They interact constantly with their environment. The quantum weirdness fades quickly under the weight of air, light, and noise. This is called decoherence, the process by which quantum systems lose their delicate superpositions and become ordinary, definite things. But the metaphor lingers because it points to something we still don't fully understand. When and how does possibility become reality? Some interpretations suggest that all outcomes do happen, that when a quantum event branches, the universe does too. One world where the cat lives, another where it doesn't. Infinite branches, each containing a version of reality shaped by a different measurement. This is the many worlds interpretation, a cosmos not of one timeline, but of countless parallel streams, born from every superposition ever collapsed. Others argue that the wave function is not real, only a tool for predicting outcomes. That quantum uncertainty reflects our ignorance, not the system's ambiguity, but the experiments resist this simplicity. Over and over, the world behaves not as if it's hiding secrets, but as if it hasn't decided what it is yet. And somewhere in this uncertainty, something remarkable happens. Superposition is not just a puzzle of particles. It is the raw material of quantum technology. Quantum computers, for example, use qubits, quantum bits that can exist in multiple states at once. Unlike classical bits, which are either 0 or 1, a qubit can be both, and every shade in between. This allows for calculations far beyond the reach of any traditional computer. It's not faster by doing one thing at a time. It's faster because it explores many paths in parallel, holding open possibilities before choosing a final answer. In that sense, superposition is not about indecision. It's about potential. The universe, beneath its surface, is not rigid and deterministic. It is supple, layered, filled with options. The particle doesn't just travel one path. It considers all of them. A decision doesn't just close doors, it opens them in other worlds. The idea that something can be many things at once may feel absurd, but it's also what makes the world fertile, creative, and endlessly surprising. When we observe a quantum system, we are not simply finding out what it is, we are participating in the process of making it real. That single point we measure, the outcome we write down, is the end of the blur. But before that, in the hush between the start and the question, lies the shimmer of superposition. It's there, right now, in the circuits of machines that may one day crack impossible problems. In the patterns of photosynthesis, which seem to use quantum paths to move energy with eerie efficiency. In the heartbeats of stars, the chemistry of thought, the boundaries of what is and what might be. A particle is many things, and for a brief, weightless moment, it is all of them. Somewhere, in the silent dark between galaxies, two particles drift apart. One heads left, the other right. Light years stretch between them. Cold, empty distance. Nothing connects them anymore, not wires, not signals, not waves. And yet, in a way that defies both logic and space itself, they are still one. This is entanglement. It begins when two quantum particles, say, a pair of electrons, are created together in a shared state. Their properties, like spin or polarization, are linked in a way that's not just complementary, but deeply woven. The fabric of their identities is shared. If one spins up, the other spins down. If one goes left, the other leans right. Not because one reacts to the other, but because both are parts of a single, indivisible quantum state, even after separation. The strangeness begins when you try to measure them. You might catch one electron here on Earth and measure its spin. The instant you do, the other electron, no matter how far it has traveled, reflects that choice. Its spin resolves to match its partner's story. No delay, no message, no crossing of time or light. It just happens. Einstein didn't like this. He called it spooky action at a distance, dismissing it as a flaw in the theory. He believed that there must be hidden variables, undiscovered rules buried inside each particle, silently dictating how they'd behave when measured. That the connection wasn't mysterious, just incomplete, a trick of ignorance, not a collapse of locality. But time and experiment had other plans. In the 1,960 seconds, physicist John Bell devised a way to test the idea. His inequalities laid a trap for hidden variables. If they existed, certain statistical patterns would appear when entangled particles were measured. But if quantum mechanics held true, those patterns would be different. Not just subtly, but fundamentally. The tests came slowly, over decades, as technology caught up to theory. But when they arrived first, tentative, then increasingly precise, they told a clear story. Bell's inequalities were violated, again and again. In labs scattered across continents, using entangled photons, electrons, even atoms, researchers found the same result. The correlations were real. The particles were not playing by classical rules. There were no hidden instructions guiding them. Their connection was genuinely non-local. Entanglement doesn't send information faster than light. It can't be used for communication in the traditional sense, but it reaches across distance in a way nothing else in physics does. It says that space, as we understand it, is not a barrier, that parts of the universe can remain deeply linked, even when torn apart. What happens to one, in a very real sense, still matters to the other. The implications are not just poetic, they are practical. Quantum entanglement is the beating heart of many emerging technologies. Quantum cryptography uses it to create perfectly secure communication, where any attempt to eavesdrop changes the system itself. Quantum teleportation, already demonstrated in laboratories, uses entanglement to transmit the state of a particle from one location to another without moving the particle itself. And quantum computers rely on entangled qubits to process vast landscapes of information in parallel. But beneath the math, beneath the equations and the devices, there's something deeply human about entanglement. The idea that connection doesn't vanish with distance, that what begins together remains together in some invisible and intimate way. You can imagine it like a pair of dancers, spinning on a stage, separate in space, yet moving in sync, choreographed not by sight but by a deeper rhythm, or two halves of a melody, scattered across the air, each incomplete without the other. When you listen to one, the other hums in reply. The particles don't send signals to each other. They don't change in response. They simply are. Coherent expressions of a single truth, revealed in two places. The universe, at its core, is not made of parts, but of relationships. And this challenges everything we thought we knew. Classical physics taught us to picture the world as a collection of separate objects, each with its own properties, each evolving in time, influenced only by its neighbors. But quantum entanglement dissolves that neat picture. It says that some systems can't be described in isolation at all, that their very meaning depends on their connection to something else. This is not just a new rule, it's a new lens. It shows us that the world is less like a machine and more like a web, a lattice of interactions, a field of correlations that stretch beyond sight, beyond time, whispering across the cosmos. Entanglement doesn't just live in particles. It lives in the laws themselves, in the stitching of space and energy and possibility. We still don't know why the universe allows this, or whether something deeper still lies beneath. Maybe one day a grander theory will reveal the architecture behind it. But for now, the effect stands unshaken, verified, confirmed, repeatable. A mystery not of doubt, but of depth. So when you look at the night sky and feel the distance between stars, between galaxies, between yourself and the rest of everything, remember this: not all distance is real. Some connections are written into the fabric. Some bonds do not stretch or fray with space. And in the quiet spaces between particles, in the intervals where cause and effect blur into something more fluid, something more complete, the universe reminds us: what is joined at birth does not forget. Picture a hill rising in the distance, a solid, immovable wall of stone. On one side, a ball rolls up toward it, slows, and comes to rest, lacking the energy to make it over. In the world, you and I know, the classical world, that's where the story ends. No matter how many times the ball rolls forward, if it lacks the force to crest the hill, it will never reach the other side. But in the quantum world, the rules begin to bend. Here, the ball isn't just a ball. It's also a wave, a swelling of probabilities, a cloud of possible outcomes. And that cloud doesn't stop at the base of the hill. It stretches forward, fading but never quite vanishing, reaching into the barrier and beyond it. That wave, however faint, means something astonishing. Even though the ball lacks the energy to climb the hill, there's still a non-zero chance it might appear on the other side. Not by going over it, not by breaking it, but by passing through. This is quantum tunneling, a phenomenon where particles cross barriers they have no business crossing, not because they break the laws of physics, but because the laws themselves are built differently at these scales. Where classical physics says no, quantum physics whispers, perhaps, and, in the right conditions, that perhaps becomes real. It isn't just theoretical. We've watched it happen. In radioactive decay, for instance, an alpha particle, a tight bundle of protons and neutrons, sits trapped inside an atomic nucleus. The nuclear wall around it is tall and steep, too tall by every classical measure. Yet sometimes, without warning, the particle appears outside, escaping as radiation. Not because it broke the barrier, but because the universe allowed it to slip through a crack that only quantum mechanics can see. It's not just rare, it's essential. Without quantum tunneling, the sun wouldn't shine. At the heart of the sun, hydrogen atoms press tightly together under immense pressure and heat. But even at those extreme conditions, the protons, the positively charged cores of hydrogen, repel each other fiercely, like charges resist. In the classical world, they should never get close enough to fuse. Yet, they do. Somehow, millions of times a second, protons overcome their mutual repulsion and merge, releasing energy that streams across the solar system as light and warmth. The reason is tunneling. Even though the protons don't have the energy to smash together outright, the wave function of each extends beyond its classical boundary. And occasionally, those extensions overlap just enough to allow fusion to occur. The protons tunnel through the repulsion barrier and meet. That meeting fuels the star. Without it, the sky would be dark. Earth would be cold. Life as we know it would never have emerged. So much from such a strange, silent mechanism. Tunneling is not reserved for the cores of stars. It happens in your electronics. In transistors, semiconductors, and scanning tunneling microscopes, devices that rely on particles sliding through barriers, making possible the machines you're using now. It happens in chemical reactions, too, where particles shift positions or bonds form in ways that would otherwise be forbidden. It may even play a a role in the enzymes of your cells, helping reactions unfold in elegant, improbable ways. At its heart, tunneling reveals something profound, that particles are not confined to the here and now. They blur, stretch, and echo. They have a presence that exceeds their boundaries, and sometimes that presence is enough to tip the scales, to slip between the lines of what should be and what is. What does it feel like to tunnel? If particles had awareness, would they sense the barrier? Would they feel resistance? Or would it be seamless, just one side of existence to the next, with no memory of the boundary crossed? There's no answer. Only the mathematics, and the experiments, and the glimmering truth they leave behind. But the implications linger. Quantum tunneling suggests that the world is not a rigid structure, but a pliable field. That what seems solid might only be mostly solid. That even the impossible has, beneath its skin, a grain of chance. That barriers, however thick, might still be crossed not by force, but by possibility. It invites us to question our own sense of limits, to wonder whether some walls in our lives, our thoughts, or our understanding might not be as impassable as they seem, whether there might be ways through that don't require breaking, only being, only extending ourselves slightly into the unknown and waiting for the rest to follow. At the smallest scale, the universe is never still. It pulses, breathes, and shifts. Particles appear and vanish, tunnel and fuse, disappear and reappear across gulfs of energy and space. Nothing is entirely bound. Nothing is entirely free. Everything exists within a spectrum of probability. A barrier may look like the end of the path, but sometimes the path goes on, quietly, invisibly, through. Imagine standing at the edge of a quiet lake, watching a single ripple glide across the surface. You can trace its curve, feel its rhythm, and if you tried hard enough, you might even guess where it came from and where it's going. But now imagine trying to do the same with a particle, not a boat or a stone or something you can touch, but a shimmering, wavering piece of the quantum world. It doesn't move like objects we know. It doesn't sit still long enough to pin down. And if you reach for it with too much certainty in one direction, you lose sight of it in another. This is the uncertainty principle. In 1927, Werner Heisenberg gave shape to an idea that had been lurking in the equations of quantum mechanics. He found that the more precisely you try to measure a particle's position in its exact location in space, the less you can know about its momentum, its speed and direction. And the reverse was just as true. The tighter you grip one truth, the more the other slips through your fingers. It wasn't a flaw in our instruments. It was a property of reality itself. This isn't just about particles being small or fast. It's not about the difficulty of observation. It's deeper than that, woven into the very structure of the quantum world. At this scale, particles are not points with perfect locations and velocities. They are described by wave functions, rippling mathematical expressions that spread through space, carrying probabilities instead of certainties. To define a particle precisely is to collapse those ripples into something narrow, and the narrower you make one aspect, the more the others stretch out in defiance. Imagine a violin string, stretched tight and plucked. If the wave is wide and smooth, the pitch is low and uncertain. If it's sharply localized, pinched, tight, and small, the pitch becomes clearer, higher, but the position of the string becomes harder to isolate. A similar tension exists in particles. Their wave-like nature means that knowing one part of their identity distorts the rest. You might think, can't we just get better tools, sharpen the microscope, cool things down, isolate the system? And we have. But uncertainty doesn't go away. It isn't about interference or noise. It's about what a particle is, or more precisely, what it isn't. A quantum particle is not a marble moving through space. It's a probability field, a cloud of maybes, and it resists being reduced to a single, exact point. This leads to consequences that are strange and unavoidable. For instance, if a particle were ever confined to an infinitely small region of space, if we tried to trap it with perfect precision, its momentum would become infinitely uncertain. It would behave wildly, leaping in unpredictable directions, as if protesting its confinement. The universe doesn't allow such strict boundaries at this scale. The closer we try to hold something still, the more fiercely it pulses with potential motion. This principle doesn't just apply to position and momentum. It echoes through other pairs of properties too, energy and time, for instance. The more precisely we define an energy level, the less certain we are about how long the system will stay in it. This is why quantum states decay, why unstable particles don't last forever, and why even a vacuum isn't truly empty. There's a flickering at the edges, a blur that never quite resolves. At the macroscopic level, the world we can see and touch, the uncertainty is so small it barely matters. You could measure the position and velocity of a baseball with extreme accuracy, and Heisenberg's limits would still be dwarfed by ordinary error. But shrink down to the level of atoms, electrons, or photons, and the uncertainty becomes the landscape. It's no longer a background hum, it's the melody. This principle also hints at why we can't predict everything, not in the way we once hoped. Classical physics promised a clockwork universe, one where, given enough data, you could compute the future with precision. But quantum mechanics tells a different story. At its root, the universe is not just unknown, but unknowable in certain ways. It doesn't hide a deeper layer of determinism. It dances in a space where questions dissolve into ambiguity. Still, uncertainty doesn't mean chaos. There's order in the probabilities. The equations are precise, the predictions sharp within their own limits. It's not that anything can happen, it's that we're always balancing between what we can know and what must remain out of reach. The structure is there, but it moves like mist. Try to grasp it too tightly, and it disperses. What's most unsettling and perhaps most beautiful is that this isn't a failure of human understanding. It's the nature of the world, a built-in softness at the edge of measurement, a curtain drawn not by ignorance, but by design. It invites a different kind of knowledge, one rooted not in absolutes, but in distributions, not in certainty, but in expectation. We learn not to demand sharp outlines, but to read the patterns in the haze, to see meaning in the scatter, rhythm in the uncertainty. And maybe, on some level, it mirrors us. How often do we try to define ourselves or others with precision, only to find that the closer we look, the more the picture changes? We too contain multitudes. We too resist being fixed in place. In the end, the uncertainty principle doesn't limit how much we can know. It defines how we must know, not as collectors of perfect facts, but as participants in a world that is alive with possibility. A world where measurement shapes truth, where observation carries weight, and where knowledge is not a snapshot, but a dance between what is revealed and what remains elusive. And sometimes, in that blur, in that flicker at the edge of knowing, we glimpse the most honest version of reality, not rigid, not complete, but open. If you could somehow drift into the vastest nothing far beyond stars, beyond galaxies, into a silence untouched by time, you might think you'd arrived at the edge of emptiness itself. No particles, no light, no matter. Just the hollow quiet of space. A perfect vacuum. But the deeper you look, the more that illusion begins to crumble. Because in quantum physics, even nothing is something, and the vacuum, it turns out, is alive. Empty space is not a blank page. It is a restless, flickering sea, a canvas not of silence, but of whispers. Within that apparent stillness, the rules of quantum mechanics allow and in fact demand that particles constantly shimmer into existence, only to vanish again a breath later. These are virtual particles, ghostly pairs of matter and antimatter, born out of the vacuum itself, existing for the briefest flickers of time before annihilating each other and fading back into the void. Not quite real, but not entirely imaginary. Not directly observable, but undeniably present. They arise because, in quantum theory, energy itself is uncertain. That same Heisenberg uncertainty principle that blurs the position and momentum of particles also applies to energy and time. If you look closely enough, for short enough durations, the conservation of energy loosens just enough to allow tiny fluctuations, tiny enough and fast enough that they escape the rule's brief loans of energy from the universe that are paid back almost instantly. It's like the vacuum is breathing, exhaling and inhaling possibilities in pulses too quick to grasp. These flickers don't behave like the particles we know. They don't travel in straight lines, don't leave tracks in detectors. They are not visitors to the universe. They are part of its backdrop, but their fingerprints are everywhere. One of the most striking places they appear is in the Casimir effect, a phenomenon that exists purely because of the vacuum's restlessness. Take two metal plates, place them very close together in a vacuum, and the sea of virtual particles outside the plates presses inward. Between the plates, certain wavelengths are suppressed. There's just not enough room for them to exist. This imbalance creates a pressure, tiny but real, pushing the plates together. It's not the force of gravity, not magnetism, just the gentle nudge of empty space proving it's not truly empty after all. They also play a role in the most precise theory we've ever built, quantum electrodynamics. The behavior of electrons, the shifting of energy levels, the structure of atoms, all are influenced by the dance of virtual particles popping in and out of existence. Without them, our predictions wouldn't match what we see. But with them, the math aligns almost perfectly, matching experiments to more than 10 decimal places. Even the light from distant stars bends around them. In the presence of intense gravitational fields like those near black holes, the vacuum becomes even more exotic. According to Stephen Hawking's work, the boundaries of black holes are not absolute. Virtual particles at the edge of an event horizon can and become separated. One falls in, the other escapes. Over time, this leakage of energy, Hawking radiation, slowly evaporates the black hole. The most massive, terrifying objects in the cosmos, fading into emptiness, undone by the quantum foam bubbling quietly at their edges. This idea that the vacuum is a seething, unstable field has even more dramatic consequences. When we calculate the energy of empty space, the sum of all these fluctuations, it comes out staggeringly large. So large, in fact, that it would cause the universe to expand at a rate far beyond what we observe. Something is off. Either the quantum vacuum energy is canceled out by some unknown mechanism, or we are missing a fundamental piece of the puzzle. This mystery, known as the cosmological constant problem, remains one of the greatest unsolved questions in physics. Why does the vacuum hold so much energy in theory and so little in practice? And yet, even in its quietest form, the vacuum may still drive. The cosmos. The faint, persistent expansion of the universe, accelerating over time, is believed to be powered by dark energy. And one possibility is that this energy isn't coming from some distant field, but from the vacuum itself. The same fabric of space that spawns ghost particles might be gently stretching the cosmos wider with every passing moment. It's almost poetic. The emptiest parts of the universe are not static. They do not sleep. They churn with uncertainty, with births and deaths that leave no trace but still shape everything. There's something deeply humbling about that. To think that what we once called nothing, a word used to describe absence, stillness, void, is, in truth, the most active background imaginable. That every atom, every light wave, every heartbeat occurs in the midst of a frothing, invisible sea. We are never truly alone in the void, not because of what we bring with us, but because the void itself is never truly empty. The quantum vacuum is a reminder that silence is never absolute, that stillness, at its core, is woven from motion, that what we cannot see and may never fully understand still holds the keys to everything we are, because sometimes the most profound forces are not the loudest or the brightest. They are the ones humming quietly beneath the surface, in the places we thought were empty. It begins not with particles, but with something deeper, more fluid, more foundational. A quiet field stretched across space and time, invisible, continuous, present even in the absence of matter. In quantum field theory, these fields are the true fabric of reality. Particles, those tiny dots we picture in orbitals or bouncing through detectors, are not building blocks themselves. They are ripples. Every type of particle, electron, photon, quark, is a manifestation of a field that exists everywhere. The electron field hums through all of space. So does the photon field, and the fields for every other particle in the zoo of matter and energy. These fields don't sit separately like islands, but overlap and intertwine, layered like transparent sheets of music. And in each field, a vibration, a quantized excitation can arise. When it does, we see it as a particle. A single photon is not a marble traveling through space. It's a pulse in the electromagnetic field. An electron is a tiny wave cresting in the electron field. Nothing solid, nothing discrete, just a ripple, a peak, a moment of energy raised from stillness. This way of seeing the universe reframes everything. Instead of thinking of the cosmos as made of particles bouncing around like billiard balls, we begin to see it as an ocean of fields in constant motion. Particles appear and disappear, not as independent entities, but as brief events, localized notes struck on the strings of reality. They emerge, interact, and dissolve back into the calm, like raindrops into water. What's remarkable is that this isn't just metaphor. It's mathematics, tested and confirmed. Quantum field theory isn't some fringe interpretation. It is the bedrock of the standard model of particle physics, the most accurate and experimentally verified framework we've ever constructed. It explains the electromagnetic force, the strong and weak nuclear forces, and the behavior of all known elementary particles with uncanny precision. Predictions made by this theory have been confirmed to more than a dozen decimal places. But the beauty of it lies not only in its accuracy, but in its elegance. When particles interact, they are not colliding objects, they are overlapping waves. One field trembles in the presence of another, exchanging energy and momentum through its ripples. These interactions are governed by symmetries, deep mathematical structures that dictate what can and cannot occur. And these symmetries give rise to conservation laws of energy, of charge, of spin. The photon, for example, is the result of requiring the laws of physics to remain the same under certain transformations in the electromagnetic field. In that sense, the existence of light is not arbitrary. It is demanded by the symmetries of the universe. Gauge symmetries, as they're called, are not just elegant, they are generative. They don't just describe the world, they create it. Quantum field theory also helps us understand why particles have mass. In a universe of pure fields, mass arises when one field, the Higgs field, interacts with others. The Higgs field, discovered in practice in 2012 with the identification of the Higgs boson, is unique. It doesn't turn off. It has a non-zero value everywhere in space, like a fog that all other particles must move through. Some pass through easily and stay light like photons, which ignore the Higgs field altogether. Others, like the W and Z bosons, interact strongly and gain mass. Mass is not an intrinsic property. It is resistance to motion through a field. In this light, particles are no longer standalone pieces, but relationships. They are defined not by what they are, but by how they dance through the medium of existence. Fields ripple into particles. particles stir new waves in other fields. The universe, then, is not built from things. It is composed of interactions, resonances, feedback. Even space itself is not empty, but alive with these fields, each one poised, even in stillness, to awaken. When two particles annihilate, it is not destruction in the classical sense. It is two disturbances in different fields, canceling each other out, their energy released, reshaped, reborn in another field. Matter transforms, but the fields endure. They are the ever-present backdrop, the unbroken substrate from which reality draws form. Quantum field theory also lays the groundwork for the dream of unification. By expressing forces as fields, physicists have been able to unite electricity and magnetism into electromagnetism. Later, that framework was extended to include the weak nuclear force in what is now known as the electroweak theory. The hope is that one day, all forces, perhaps even gravity, will be shown to be different notes in a single, underlying field. A grand symphony, still partly hidden, but there are limits too. Quantum field theory works best where gravity is weak. When gravity becomes strong near black holes, at the birth of the universe, the equations fray. To reconcile them, we would need a quantum theory of gravity, something still out of reach. String theory, loop quantum gravity, and other candidates offer ideas, but the definitive answer remains elusive. Still, even without it, field theory tells us something profound, that what we take to be things are merely excitations in something more continuous, that the illusion of separateness is just that, an illusion. Everything that is connected at the level of fields, bathing the universe in a shared fabric of possibility. It means that you and I, and the stars and stones, are all ripples in the same ocean, momentary rises in an unbroken sea. And in that vision, there's a kind of stillness, a kind of peace. The world isn't made of fragments, it is made of waves. Somewhere, drifting through the stillness of the cosmos, a single electron pulses along its path. Invisible to the eye, yet utterly real, it carries charge, mass, and the quiet legacy of the field from which it rose. But hidden in the laws that birthed it, nestled in the symmetries of nature, lies its twin, a reflection not just in shape, but in essence. This is the positron, the electron's opposite, its antimatter counterpart, equal in mass, but opposite in charge. A mirror version, moving in step with a rhythm just slightly out of phase. For every particle we've found, nature seems to allow for a partner, an anti-self, not just a theoretical quirk, but a built-in requirement of the equations that govern quantum fields. When Paul Dirac worked through the math of relativistic electrons in the 1920 seconds, he stumbled upon a strange solution, a particle that behaved like an electron, but with a positive charge. At first, it seemed like a mistake, but the universe rarely makes mistakes without purpose, and within a few years, that ghost in the math became real, discovered in cosmic rays and captured in detectors. Antimatter was no longer fiction. It turns out that the vacuum so deceptively quiet can give rise to both matter and antimatter, spontaneously, in pairs. When energy is concentrated enough, it condenses into mass, as Einstein showed us with E equals mc squared. But mass can't form alone. The laws of physics demand balance. So, out of the same spark of energy, one particle and one antiparticle are born together, equal and opposite. A photon with enough energy, when passing near an atomic nucleus to conserve momentum, can briefly become a pair, an electron and a positron, spiraling apart like dancers flung from a single step. This process, pair creation, is one of the most elegant demonstrations of the quantum world's symmetry. From light, mass emerges. From energy, identity, not just something from nothing, but two somethings from balance, as if the universe insists on fairness even in its smallest acts. But the story of antimatter is not one of peaceful coexistence. When a particle meets its antiparticle, the reunion is brief and intense. Their encounter erases them both in a flash of light, a pure conversion of mass back into energy. Annihilation, we call it. Though it's not destruction in the classical sense, it's transformation. The energy remains, but the identities dissolve. The electron and the positron vanish, replaced by photons streaming outward, silent witnesses to a perfect symmetry resolved. This dance of creation and annihilation plays out all around us. In the high atmosphere, cosmic rays strike atoms and spark new pairs into existence. In medical imaging, positron emission tomography relies on radioactive isotopes that emit positrons, which quickly meet electrons and vanish, producing gamma rays that let us see the body's inner workings. In laboratories, we build traps for antiparticles, suspending them in electromagnetic cages, watching them hover just long enough to glimpse the rules of their nature before they disappear again. And yet, for all this symmetry, there's a puzzle. If pair creation is so balanced, if every particle emerges with a mirror sibling, then why does the universe exist the way it does? Why does matter dominate while antimatter seems scarce? After the Big Bang, there should have been equal parts of both, but something tipped the scales. Some tiny asymmetry, still not fully understood, led to a universe where matter stayed and antimatter mostly vanished. A cosmic imbalance born from a symmetrical law. The silence of antimatter is perhaps the loudest unanswered question in modern physics. Some theories suggest that antimatter didn't vanish, but separated, drifting into corners of the universe where matter is rare. If that's true, there could be stars made entirely of antimatter, whole galaxies with anti-atoms forming anti-planets under anti-suns, but we've never found them. When matter and antimatter meet, they leave behind a signature burst of radiation, and the sky is quiet. Others think the imbalance was born in the early moments after the Big Bang, when the forces of nature were still untangling themselves. Tiny violations of symmetry, perhaps in the weak force, might have favored matter just slightly more than antimatter, tipping the balance with barely a whisper. Whatever the cause, it left us here, made of matter, in a universe that once could have ended in light. Still, antimatter is not just a mystery, it is also a tool. In experiments at CERN and other particle labs, we create and study it to test the deepest symmetries of nature. We watch how it behaves, how it decays, how it bends in magnetic fields. We ask whether it falls in gravity the same way matter does. And with each observation, we probe the boundaries of the known, chasing the contours of reality's mirror. One day, we might learn to harness it. The energy released from matter-antimatter annihilation is staggeringly dense, far beyond chemical reactions or even nuclear fusion. A single gram of antimatter, meeting its counterpart, would release energy equivalent to a nuclear bomb. But producing and storing even micrograms is beyond our reach. For now, antimatter is elusive, expensive, and fleeting. It resists containment. It wants to vanish the moment it touches the world. And yet, in every fleeting positron, in every delicate dance of creation and annihilation, we see a truth that humbles and inspires, that identity is not fixed, that even opposites arise from the same field. That symmetry, while beautiful, is not always balanced in the ways we expect. We live in a world where particles have shadows, where every something is born with an echo, and though those echoes often disappear before they can be heard, they remind us of a deeper harmony woven into the quantum fabric. In that harmony, creation and destruction are not enemies, but partners. Each breath of matter is matched by a whisper of its twin, and the universe, in all its brilliance, is still humming with the music of both. In the world we know, time flows like a river. It begins at a source we cannot return to, and carries us forward, moment by moment, toward a future we cannot yet see. The past is fixed, the present fleeting, and the future undefined. This is the rhythm we live by, the ticking of clocks, the aging of bodies, the decay of stars. We believe in the arrow of time, drawn by entropy, shaped by memory. But in the quantum world, that arrow softens. It flickers, and in some experiments, it bends. At the level of fundamental particles, the laws of physics are curiously time-symmetric. The equations don't mind whether you run them forward or backward. If you were to watch a single electron interact with another, or a photon slip through a crystal, and then reverse the footage, it would still make perfect sense. The math holds. The processes are reversible. There is no preferred direction. Time, it seems, doesn't care which way it goes, and yet our experience insists otherwise. We see cups fall and shatter, never rise and reform. We remember the past, not the future. We age in one direction. But these are not the results of quantum law. They are the echoes of complexity, the rise of entropy, the loss of order. At the microscopic level, the rules remain agnostic. They describe a universe where cause and effect are not strictly chained by chronology. And nowhere is this more unsettlingly revealed than in the phenomenon known as delayed choice. The delayed choice experiment, originally proposed by physicist John Wheeler, is an extension of the famous double-slit experiment. In the traditional setup, a photon passes through a pair of slits and creates an interference pattern on a screen, as if it traveled through both slits at once, behaving like a wave. But when we place a detector to observe which slit it goes through, the interference vanishes. The photon chooses a path, acts like a particle, and the wave collapses. Observation changes reality. In the delayed choice version, the twist is timing. The decision to observe or not observe which slit the photon traveled through is made after the photon has already passed through the slits, but before it reaches the screen. This means that the photon's behavior at the slit's wave or particle is determined by a choice made in the future. It's as if the act of measurement reaches back in time and rewrites the photon's history. You can set up the experiment so that your decision to insert or remove the detector is made after the photon has passed the critical point where it would have had to decide how to behave. And yet, the outcome still depends on your choice. It's not that the photon waited, it's that its entire history reshaped itself to match your future action. The path it took, the nature it expressed, the pattern it left behind all seem to respond not to the present, but to the context of measurement, even if that context comes later. This doesn't mean the future literally causes the past, but it suggests something subtler. In quantum mechanics, the properties of a particle are not fixed until they are measured. Until that moment, they exist as probabilities, overlapping possibilities, superpositions of paths. When we measure, we don't just uncover a pre-existing reality, we help define it, and the effects of that definition ripple backward through the particle's quantum history, resolving ambiguity not only forward, but back to the point of origin. Some interpretations, like the transactional interpretation, imagine quantum events as standing waves of possibilities, where waves travel both forward and backward in time. A kind of handshake occurs between the emission of a particle and its detection, a meeting across time that settles what actually happened. It's a strange idea, but one that preserves the math, the symmetries, and the outcomes we observe. Others invoke the block universe, a view from relativity, where past, present, and future all exist at once, laid out in four-dimensional space-time. From this perspective, time is not a flowing river, but a landscape. We, as observers, experience it one moment at a time, like walking through a forest where only the path beneath our feet is visible. But the forest is already there, the trees ahead and behind, equally real. In such a view, quantum uncertainty collapses not through forward causality, but through the consistency of the whole. Events line up, not because they are pushed by the past, but because they must fit together in a coherent tapestry. These ideas challenge our deepest intuitions. We want time to be simple, linear, obedient. We want the past to stay still and the future to wait its turn. But quantum physics suggests that the fabric of reality is far more flexible, more interwoven than our clocks or calendars reveal. And yet, even within this strangeness, there is a kind of logic, a balance. The probabilities always add up. The experiments, repeated countless times, yield results that are consistent, predictable, beautiful in their structure. We are not left in chaos. We are given a glimpse of order, one step removed from certainty. What does it mean for us to live in a world where the future might influence the past? Perhaps it means that the universe is less like a machine and more like a story, a narrative unfolding, not sentence by sentence, but as a whole, where each chapter reflects the others, where meaning arises not only from the beginning, but from the ending too. In the quantum world, time does not march, it resonates. And in those echoes between choice and chance, between past and possibility, we find a reminder that reality is not built from simple bricks, but from waves of connection, entangled not only across space, but across the moments that define us. In the strange theater of the quantum world, where particles vanish into probabilities, and reality reshapes itself with every act of observation, there is a phenomenon that seems to stretch the limits of imagination even further, a kind of magic not bound by distance, speed, or time. It's not teleportation in the way science fiction describes it. No one is stepping into a shimmering pod and reappearing across the galaxy. Instead, it is something subtler and stranger. Not the movement of matter, but the transmission of identity, a transfer of essence, without anything physically crossing the space in between. This is quantum teleportation, and it begins not with motion, but with entanglement. Imagine two particles, photons, perhaps entangled in such a way that their states are perfectly correlated, even though neither has a definite state of its own. Spin, polarization, momentum, these are not assigned to each particle individually. Instead, they are shared, interdependent. The particles form a single system, stretched across space, where what happens to one affects the other, instantly, no matter the distance. This connection is not a signal. It does not travel. It simply exists, like a thread woven through the fabric of the universe. Now picture a third particle, call it a holding some unknown quantum state. This particle is not entangled with the others. It carries information, not in bits and bytes, but in qubits, where it can exist in multiple states at once, suspended in delicate superposition. Our goal is to transfer the state of particle A to a distant particle, say, particle B, without ever physically moving, A, and without ever knowing exactly what its state is. At first glance, this seems impossible. In classical terms, if you wanted to send someone a message, you'd simply copy it. But in quantum mechanics, the no-cloning theorem forbids such copying. You can't make an exact replica of an unknown quantum state. To learn the state in full, you'd have to measure it, and the act of measurement destroys its original superposition. The very thing you want to transmit would be lost in the act of reading it. But here, quantum entanglement offers a loophole not by copying the state, but by transferring it. The process begins by entangling particles B and C and sending particle B to some distant location. Particle A, whose state we wish to teleport, remains near C. Then, a joint measurement is made on A and C, a special kind of quantum comparison known as a Bell state measurement. This measurement doesn't tell us the individual states of A or C. Instead, it collapses the joint system into one of several entangled combinations, effectively entangling A and C while also breaking C's connection with B. But in that moment, something extraordinary happens. The original state of A is destroyed, absorbed by the measurement, but the result of that measurement, combined with the prior entanglement between C and B, has altered the state of B. It now holds the information that was once part of A, the identity of A, its spin, its superposition, its quantum fingerprint, has been transferred to B, not by a signal sent across space, not by matter in motion, but by the hidden rules of quantum correlation, by a bridge that was built before the process even began. To complete the process, the result of the measurement, 2 classical bits of information, is sent from the original location to the destination. Once those bits arrive, a simple operation is applied to B to finalize the teleportation. And just like that, the state of A reappears in B, perfectly recreated, while the original vanishes without a trace. It's a delicate, almost ritualistic exchange, a dance between uncertainty and certainty, collapse and correlation. The information is not duplicated. It is not copied. It is disassembled in one place and reassembled in another. Quantum teleportation is less about transport and more about transformation. And despite its elegance, this is not theory alone. It has been demonstrated in laboratories many times over the last 2 decades. Scientists have teleported photons across rooms, across fiber optic networks, even between satellites and ground stations. In 2017, Chinese researchers used a satellite named Misseus to teleport quantum information between Earth and orbit, over 1,200 kilometers apart. The technology is still young, still fragile, but it marks the beginning of a new kind of communication, one not limited by wires or waves, but shaped by the deeper, stranger architecture of reality itself. There are limits, of course. Teleportation cannot be used to send information faster than light. The classical bits that complete the process must still travel through normal space, bound by the speed limit of the universe. But the heart of the transfer, the shift of quantum state, happens instantaneously, guided by correlations that know no distance. Einstein called it spooky action at a distance. But to quantum physicists, it is simply the way the world works when you let go of locality. This phenomenon has vast implications not only for communication, but for the future of computing. Quantum teleportation may one day serve as the backbone of a quantum internet, linking entangled nodes across the planet in a network more secure, more private, and more powerful than anything we've yet imagined. It may allow quantum computers, each holding fragile states within isolated environments, to share and transfer information without risk of observation or corruption. And yet, beyond the technology, there is something deeply poetic about it. That a thing can vanish in one place and be reborn in another. That identity is not tied to matter, but to patterns, relationships, and context. That what makes something what it is, its inner logic, its hidden code, can leap across space, unbroken, untouched. We are not teleporting bodies, we are teleporting selves. And in doing so, we are learning something about the nature of being not as a fixed location, but as a wave that can ripple from one corner of the cosmos to another, carried not by motion, but by meaning. In the quantum world, information is sacred. It cannot be cloned, it cannot be lost, but it can, under just the right conditions, disappear from here and reappear there, like a whisper riding the wind of entanglement. A message from the universe that distance is not the barrier we once believed it to be. Somewhere, in a version of this moment, not far removed from the one you're in now, you made a different choice. Maybe you paused this video instead of continuing. Maybe you got up for a glass of water. Maybe, without even realizing it, a single particle in your brain flipped one way instead of the other, and with that, a new branch of reality bloomed into existence. You didn't feel the split. You didn't hear the sound of a universe dividing. But according to one of the most radical interpretations of quantum mechanics, it happened all the same. The many worlds interpretation doesn't claim there are just alternate realities. It suggests that every quantum event, every time a particle's behavior is uncertain and could resolve in more than one way, the universe doesn't pick one outcome. It picks all of them. And rather than choosing one path and discarding the others, reality itself divides. The universe branches, endlessly, effortlessly, fracturing into parallel timelines where every possibility plays out. Each outcome is real, each just as valid, each just as complete, and you, or a version of you, continues in all of them. At first glance, this feels more like mythology than science. The idea that there are infinite copies of you, living slightly different lives, making different choices, walking down paths you never took, is the kind of notion usually left to speculative fiction. But in the halls of theoretical physics, it remains one of the most persistent and mathematically coherent responses to the strangeness of quantum collapse. To understand where it comes from, we return once more to the double-slit experiment. A particle, like an electron, seems to pass through both slits at once until it's observed. Then it chooses a path, and the interference pattern vanishes. This act of observation, of collapsing a wave function into a single measurable reality, has puzzled physicists for decades. What counts as observation? Why does the universe wait for us to look? In the 1,950 seconds, a graduate student named Hugh Everett proposed an answer. What if the wave function never collapses? What if, instead, it continues unfolding, evolving deterministically, splitting into multiple branches where each possible outcome is realized? From this perspective, the act of measurement doesn't destroy possibilities, it multiplies them. When you look at the electron, your own quantum state becomes entangled with it. In one world, you see the electron go left. In another, you see it go right. Each version of you follows a different path, unaware of the other's existence. The universe doesn't choose. It becomes both. This interpretation removes the need for a special role of the observer. It keeps the mathematics of quantum mechanics pure and unbroken. There's no randomness, no collapse, just the natural unfolding of the universal wave function, splitting reality like a tree growing new branches, one for every possible twist and turn. But if this is true, it leads to breathtaking consequences. Every decision you've ever made, every coin toss, every dice roll, every moment of quantum uncertainty has spawned countless new worlds. In one, you moved to a new city. In another, you never met the person who changed your life. In yet another, you did everything the same, but the light hit your face a fraction of a second earlier, and the breeze outside blew just slightly colder. And it doesn't stop with you. There are worlds where the dinosaurs never went extinct, where stars formed in different places, where Earth never cooled, where physics itself unfolded in slightly altered ways. Every quantum fluctuation in the early universe could have sent reality spinning in a new direction. The multiverse, under this view, is not a distant theoretical realm. It's the immediate, ever-branching structure of all that is. Of course, we never perceive these other versions directly. We're confined to the thread we're on, unable to leap to neighboring timelines. The other yous are sealed away by decoherence, a process that ensures quantum branches don't interfere once they've diverged. It's not that the other paths don't exist, it's that they've become, for all practical purposes, invisible. Still, traces of this vast structure show up in the math. When we calculate the probability of an outcome, we're measuring the amplitude of all the possible branches it occupies. The universe, in a sense, is constantly humming with alternatives. We live in the interference pattern of realities we cannot see. This idea can feel disorienting, even overwhelming. It suggests that our sense of identity, our belief in a single, continuous self, is just one path among infinitely many. That every version of you that could exist does. That the you reading these words is not the only one. Others sit beside you in adjacent worlds, a breath away, divided only by the finest line the cosmos can draw. And yet, there is something comforting in it too. It means that no possibility is ever truly lost, that every dream you let go of, every road not taken, still blooms somewhere. It means that the universe is richer than we know, not just in stars and galaxies, but in stories, in choices, in lives lived out to their fullest in places we'll never touch. Whether many worlds is real in a physical sense is still debated. There's no experiment yet that can confirm or deny it outright. Some physicists find it elegant and natural. Others find it excessive too many universes to explain a single observation. But mathematically, it fits. And conceptually, it reminds us that reality is not obligated to match our intuition. We evolved to navigate one world, but quantum mechanics suggests we might live in many. So the next time you make a choice whether to speak or stay silent, to turn left or right, to listen a little longer or drift off to sleep, remember this. In some other version of this very moment, you chose differently. And that other you is out there, quietly living a life you can only imagine. Not a ghost, not a fantasy, but a reflection in the infinite mirror of the multiverse. In the early morning hours, when the light begins to filter softly through the canopy of a forest, birds stir in their nests and tilt their heads toward the sky. With no compass in sight, no visible signs to guide them, they launch into flight and begin a journey that spans continents. These migratory paths are not learned through maps or stars alone. Instead, something far stranger guides them. Something humming quietly beneath the surface of biology, reaching all the way down to the quantum level. Quantum biology is the idea that life itself, messy, warm, and chaotic as it is, might use the subtle rules of the quantum world to function more efficiently, more precisely, more mysteriously than we ever imagined. For a long time, physicists believed quantum effects only mattered in clean, cold, isolated environments, laboratories with tightly controlled conditions. Certainly not inside the damp interior of a bird's eye or the tangled green machinery of a leaf. But nature, it seems, has found ways to use even the strangest tricks of physics in its most delicate work. And one of the most compelling examples lies in the migration of birds. European robins, for instance, are able to detect the Earth's magnetic field with extraordinary precision. This sense, called magnetoreception, allows them to navigate vast distances during seasonal migrations, but the mechanism behind it remained elusive for decades. Then, researchers proposed a radical idea, that birds might be seeing the magnetic field through quantum entanglement. Inside their retinas, certain molecules may form pairs of electrons known as radical pairs. When struck by light, these electrons become entangled, joined in a delicate, invisible connection. Their spins respond to the orientation of the Earth's magnetic field, changing the chemical behavior of the molecule. This, in turn, subtly affects the bird's vision, overlaying a faint, shifting pattern that aligns with magnetic north. The bird doesn't consciously see it, but it follows it all the same. This would mean that a robin's sense of direction is built not on instinct alone, but on quantum phenomena unfolding inside its cells. A quiet dance of particles, coordinated across space without touching. Every beat of its wings, every turn in the sky, guided by something as intangible as entangled spins. And it's not just birds. In the green heart of a leaf, where sunlight spills down in golden waves, another quantum process may be at work. Photosynthesis, the process by which plants turn light into usable energy, is astonishingly efficient. When a photon is absorbed by a pigment molecule in a chloroplast, it excites an electron, starting a cascade of energy transfer that moves through a complex network until it reaches the reaction center. For a long time, scientists assumed this energy simply hopped from molecule to molecule, bouncing randomly until it arrived. But experiments using ultra-fast lasers revealed something different. The energy appears to explore multiple paths at once, in a kind of quantum superposition. It flows like a wave, not a particle, sampling all routes simultaneously and selecting the most efficient one. It's as if the leaf is thinking in probabilities, not choosing a path, but allowing all possibilities to coexist before settling into the one that works best. A quiet optimization process, playing out beneath our feet and above our heads, in every leaf that shimmers in the breeze. Even our own bodies may not be exempt. The human sense of smell is something we often take for granted, intuitive, invisible, and deeply emotional. But the way we detect different molecules has long been a mystery. The prevailing theory held that each odorant molecule fits into a receptor in our nose like a key in a lock. But this idea struggles to explain why molecules with similar shapes can smell completely different, and others with different shapes can smell the same. An alternative theory suggests that smell may depend not just on shape, but on quantum vibration. According to this idea, when a molecule enters a receptor, electrons within the receptor can tunnel across a small gap if the molecule vibrates at the right frequency. This quantum tunneling depends not on the physical fit, but on the molecular signature, the way atoms within the molecule jiggle and hum. In this way, our noses might be listening as much as they are feeling, sensing the music of molecules rather than their forms. These ideas are still controversial. Quantum effects are fragile. They decohere quickly in messy environments. And yet, life seems to have found ways to protect and harness them, to build with them, sense with them, navigate with them. Evolution, over billions of years, may have stumbled upon tricks that physicists are only now beginning to understand. There's something beautiful about this, that the same rules that govern the flickering of particles and the interference of waves also shape the flutter of wings, the turning of leaves, the scent of a rose. That deep within the machinery of life, the universe is whispering its most subtle truths, and living things, birds, plants, even you are listening. Quantum biology doesn't claim that all of life is quantum. Much of it, perhaps most, can be explained through chemistry and classical physics. But it suggests that at key moments, nature dips into the quantum well, that in certain places, under just the right conditions, life gets strange. And when it does, the boundary between physics and biology, between matter and mind, grows thinner than we ever thought possible. A robin turning in flight, a leaf catching the sun, a memory sparked by a single breath of perfume, all, perhaps, humming with the rhythms of the quantum world. In the quiet hum of tomorrow's machines, something different is stirring. Not just smaller transistors or faster processors, not simply more of the same, but a new kind of intelligence, one that doesn't march forward step by step, but grows in all directions at once. Where classical computers see the world in bits, flipping neatly between ones and zeros, quantum computers see the soft shimmer of possibility. They think in superpositions. They solve by exploring. And at the heart of this revolution is a new kind of logic, the qubit. A classical bit is simple. It's either on or off, black or white, yes or no. Every calculation your phone makes, every picture it shows, every sentence you type, is built from long chains of these tiny switches, and they've served us well. But as we push closer to the physical limits of miniaturization, we're beginning to ask a new question, not how small can we make our machines, but how strange. Quantum computing doesn't throw out the rules of logic, it expands them. Instead of binary bits, it uses qubits, quantum bits that can exist in a state of 0, 1, or both at the same time. This isn't just poetic language. It's a real, measurable property of quantum systems. Through superposition, a single qubit can hold a blend of states, weighted by complex probabilities, until it is observed. When you measure it, the wave collapses into one outcome, but until then, it holds a spectrum of truths. And when qubits are entangled, the magic deepens. Their states become linked, so that the behavior of one instantly influences the other, no matter the distance. This creates a computational space, not just wider, but exponentially richer. A classical system with 3 bits can represent 8 combinations, 0, 0, 0, through 111, but only one at a time. A quantum system with 3 qubits can hold all 8 combinations simultaneously, interwoven into a single evolving wave function. The result is a machine that doesn't just try one answer after another. It tries all possible answers at once, folding the space of possibilities into a single operation. It doesn't always solve problems faster, but for certain classes of problems factoring large numbers, searching unsorted databases, simulating molecules, it opens doors that were previously sealed shut by time. This isn't just faster computing, it's a new kind of thought. The first real applications of quantum computing may not look like science fiction. They may hum quietly in research labs, solving equations for chemistry and physics that classical computers could never crack. Already, quantum simulations are helping us understand protein folding, photosynthesis, and superconductivity. They may one day unlock new drugs, clean energy, or materials that defy our current understanding of conductivity and resistance. And yet, to build a quantum computer is to fight a gentle war against nature. Qubits are delicate. They must be isolated from noise, kept near absolute zero, suspended in finely tuned environments where any disturbance, heat, light, vibration, can cause them to decohere. The challenge is not just to create superposition, but to preserve it long enough to be useful, to keep the quantum wave alive while it does its work. Different technologies are racing toward this future. Some use trapped ions held in electric fields. Others use superconducting circuits, where current flows with zero resistance. Still others rely on photons, moving at the speed of light through carefully structured optical paths. Each approach has its strengths and challenges, its own balance between stability, scalability, and control. And yet, despite the obstacles, progress continues. In 2019, Google's quantum processor, Sycamore, performed a task in 200 seconds that would take the most powerful classical supercomputers thousands of years. The task itself was narrow and tailored, but it marked a milestone: quantum supremacy, where a quantum device performs something no classical computer can match. But supremacy isn't utility. The next frontier is fault tolerance, building quantum systems that can detect and correct their own errors, operating reliably for longer durations and more complex tasks. It's a steep climb, one that will require not just advances in hardware, but new algorithms, architectures, and ways of thinking. Because programming a quantum computer isn't like writing normal code. You don't just tell it what to do. You shape a landscape of probabilities, guiding waves through interference patterns, designing circuits that fold space and time in subtle, often counterintuitive ways. It's part physics, part poetry, a collaboration with uncertainty. And once scaled, these machines could change everything. Cryptography, the very foundation of digital security, is built on mathematical problems that quantum computers could unravel with ease. Encryption methods that would take classical systems millions of years to crack could fall in hours. But quantum computers also promise new, unbreakable methods of encryption based not on problems, but on physics itself. Keys that can't be copied. Messages that vanish when eavesdropped upon. In the world of finance, logistics, climate modeling, artificial intelligence, quantum computing offers tools for optimization and prediction that exceed what any silicon chip can offer. It's not that it will replace classical computers. It will sit beside them, like a new organ in the global brain. But beyond all the practical applications, there is something profoundly philosophical about this shift. That at the root of information, at the place where logic becomes matter, we find not certainty, but ambiguity. Not black or white, but a shimmering cloud of maybes. That the future of computing depends not on eliminating uncertainty, but embracing it, riding the wave, rather than collapsing it. And in doing so, we may come to see our own thinking in a new light, not as a series of choices, one after another, but as an evolving field of potential, a space where ideas exist in superposition, waiting to be observed, selected, shaped. Just as a qubit holds many truths before it is measured, so too may our minds be capable of holding many futures before we act. Quantum computing is not just a new tool, it's a new mirror. And what it reflects back is not just a smarter machine, but a deeper understanding of what it means to know, to choose, and to imagine. At the edge of a river, where moonlight dances in ripples over water, you might toss in a pebble and watch the waves scatter. They move outward in perfect symmetry, cresting and falling, overlapping in soft interference patterns that shimmer and spread. Now imagine doing the same, but instead of a single pebble, you toss in 1,000, all at once, each causing its own ripples. Eventually, the patterns blur, the waves tangle, the symmetry fades, and all that's left is a surface that looks still. Again, the interference is still there, hidden, but lost to the eye. This, in many ways, is decoherence. It's the reason the quantum world, so strange and wild beneath the surface, seems so calm and familiar when we look around. Quantum mechanics tells us that particles can exist in multiple states at once, that an electron can be in many places, a photon can take many paths, and a cat, at least in theory, can be both alive and dead in the same breath. And yet, when we open the box, we never see the superposition. We see a single outcome, one state, one reality. The wave collapses. The possibility becomes history. But why? The answer is not that quantum rules stop working at larger scales. It's that those delicate states of superposition are incredibly fragile. They require isolation, silence, a kind of quantum stillness that our everyday world doesn't offer. The moment a quantum system becomes entangled with its environment, when it touches air, heat, light, noise, the superposition begins to unravel. Not because it's destroyed, but because it spreads. The quantum state, once neatly contained, becomes a ripple that interacts with countless other ripples, and in doing so, it loses its ability to interfere with itself. This is decoherence. It doesn't mean the quantum weirdness is gone. It means it has diffused, dissolved into the greater sea of the world. The system is no longer isolated. It's become part of the environment. And once that happens, the fragile interference patterns that define quantum behavior become impossible to recover. Imagine a violin playing a pure, single note in an empty hall. You can hear every vibration, every overtone, perfectly. But now place that violin in the middle of a bustling street. The note still exists, it's being played, but you can't hear it. The noise has overwhelmed it. The clarity is lost. Not because the violin stopped playing, but because the sound has mixed into everything else. So it is with quantum systems. A qubit in superposition can hold multiple possibilities, dancing between them like a coin spinning in midair. But let it interact with just one stray particle, one photon, one whisper of heat, and the coin lands. Not because it had to, but because the environment chose for it. Or rather, the environment entangled with it, turning a private uncertainty into a shared, irreversible history. This is why we don't see quantum superpositions in cats, or chairs, or people. Not because the rules change, but because the complexity overwhelms the coherence. The larger a system becomes, the more paths there are for it to interact with its surroundings. The more quickly its delicate quantum state leaks into the world, bleeding information into every corner of space. And once that happens, the system becomes classical, not because it lost its quantum nature, but because its quantum signature has been smeared so widely it can no longer be distinguished. In a sense, Decoherence is a translation, a transformation from the language of maybes into the language of is. It doesn't erase the other paths. It simply hides them, buries them in entanglement so deep and intricate that they might as well not exist. This also explains why building a quantum computer is so hard. To perform quantum calculations, we must preserve coherence across many qubits, keeping them entangled, isolated, and controlled, all while preventing the outside world from touching them. Every vibration, every stray electron, every flicker of thermal noise is a threat, a possible source of decoherence, like trying to balance soap bubbles on a wire in a hurricane. But decoherence is not the enemy. It's the bridge between the quantum and the classical. It's the process that allows quantum phenomena to create stable, reliable experiences. Without it, there would be no memories, no records, no definite outcomes. The world would shimmer forever in uncertainty, never settling into the solid, shared stage we live our lives upon. And though we often think of it as a loss, the collapse of beautiful possibilities into a dull, single truth, it is also a kind of creation. Out of quantum ambiguity emerges classical reality. Out of superposition comes story. In this way, decoherence may be what allows the universe to remember, to hold on to outcomes, to build time itself. Because memory is decohered quantum information. It's what the environment has absorbed and kept. The photon that bounced off your face and into someone's eye. The heat that left your coffee and drifted into the air. The marks left in dust, in sound, in thought. Every observation we make, every experience we have, is shaped by decoherence. It is the quiet force that draws the curtain closed after the wave has played its scene. And yet, even now, in carefully prepared labs, in the silence of cryogenic chambers and electromagnetic shields, we can watch coherence stretch its delicate thread. We can build systems where superposition lives long enough to be useful, long enough to whisper back from the edge of the classical world and remind us that beneath the certainty we see, uncertainty still breathes. So when you look around and see solidity trees standing still, clocks ticking forward, choices made, and consequences set in motion, remember that this ordinary world rests on extraordinary rules. Rules that allow particles to dance in possibility until the very moment they are touched. Rules that let the universe write its story one page at a time out of ink made from probability. Decoherence is not the end of the quantum tale. It is the part where it becomes ours. Far below the things we can see, beneath the sweep of galaxies and the hum of molecules, beneath even the most delicate whispers of atoms and light, there lies a boundary, a floor so unimaginably small that it might not be space at all, but something stranger, an edge, a grain, a shimmer in the very fabric of what we call reality. This is the Planck scale, a place where distance, time, and energy reach their most fundamental form, where the smooth illusion of the universe begins to crack, revealing the pixelated substrate beneath. To get there, we first need to let go of the ordinary. Our minds are trained to think of space as continuous, like an ocean or a canvas, something that can always be divided, sliced thinner, split again. A meter becomes a centimeter, becomes a millimeter, becomes a micron. But at the Planck length, roughly 1.6x, 10 to the power of negative 35 meters division stops. Not because we can't see smaller, but because there may be no smaller to see. Below this length, the very concept of position might no longer make sense. It's as though reality, when examined under the highest possible magnification, resolves into a grainy, flickering static. The Planck time, about 5.4x, 10 to the power of negative 44 seconds, is just as profound. It marks the smallest unit of time that might have meaning. Any attempt to measure something that happens faster would require so much energy that it would collapse into a black hole. In that sense, the Planck scale isn't just small. It's a kind of boundary between what can exist and what cannot. To touch the Planck realm is to confront the limits of knowledge itself. Classical physics offers a smooth, predictable world, an arena of curves and constants, of friction and force. Quantum physics shakes that world, showing us that particles don't sit still, that energy fluctuates, that certainty is a luxury we no longer get to keep. And general relativity, Einstein's masterpiece, shows us that space and time bend and twist under the influence of mass and energy. But these two great theories, quantum mechanics and relativity, disagree violently when brought to the Planck scale. There, the equations explode, singularities bloom. Space-time becomes turbulent, not smooth. Gravity and quantum mechanics clash like mismatched puzzle pieces, refusing to fit. What emerges is not a gentle fabric, but a roiling foam, a landscape where distance and duration lose their meaning, where black holes are born in the tiniest flickers of existence and then evaporate before they can be named. Physicists call this quantum foam, a seething churn of uncertainty that underlies all things. At this level, space may not be a thing that stretches, it may be something that emerges, a property, not a backdrop. Time may not tick forward, it may bubble, loop, or dissolve entirely. And we've never been there, not even close. The energies required to probe the Planck scale are so vast that no particle accelerator on Earth, not even those we can imagine centuries from now, could reach them. To test the structure of reality at that level would require a collider the size of the galaxy running at full tilt. The Big Bang may be the only moment that ever truly touched this depth. And yet, we see hints in the way black holes behave, in the math of string theory and loop quantum gravity, in the strange symmetries of particles. We chase the Planck scale, not with machines, but with equations, with thought experiments and ghostly traces left in cosmic radiation. We search for the imprint of this scale in the oldest light in the universe, hoping it carries the fingerprint of a deeper truth. Because if the Planck scale is real, then everything above it is emergent. Space as we know it might be built from quanta-discrete packets that stack together like bricks to form distance. Time might be the result of deeper processes, pulsing beneath our awareness. The cosmos, vast and ancient, could arise from something far simpler. An algorithm, a vibration, a pattern. It's as if the universe is a mosaic, and we've only just begun to notice the tiles. The Planck scale also represents a great philosophical pivot. For centuries, science has marched inward, peeling back the layers of the small, cells to molecules, molecules to atoms, atoms to quarks. We've built ever sharper tools to peer into the heart of matter. But the Planck length says, this is the end of the trail. You can go no further. Not because we aren't clever enough, but because nature itself has drawn a line. Beyond it, questions shift. They are no longer about what is inside, but about how the inside came to be. Not about things, but about principles. The Planck scale is where ontology becomes architecture, where the universe reveals that it may not be a place, but a process. Some theories propose that space and time are born from entanglement, from quantum information shared between bits of reality. Others suggest that space-time is emergent from more abstract geometries, twisting and curling in invisible dimensions. And some say that perhaps there is no space, no time, only relations, only events, only structure. The Planck scale doesn't just reshape physics, it reshapes what we mean by real. Because if the universe is built on quantum fields and uncertainty, and those fields are themselves structured on a grid smaller than we can ever touch, then our familiar world of shapes and colors and rhythms is not fundamental. It is the foam on the crest of a deep ocean, a kind of projection, a shadow cast upward from the smallest scale imaginable. And yet, from this unknowable basement emerges everything: the stars, the oceans, the touch of a hand, the beat of a heart. All of it, somehow, constructed from something more elemental than matter. The Planck scale reminds us that the universe doesn't owe us clarity, that beneath the music of physics lies a silence we may never break. And in that silence, there is something sacred, something humbling, a whisper that says, "Here is where you stop." But even as we pause at that edge, we listen. And somewhere in that listening, perhaps we begin to hear the beginnings of a new kind of understanding, one built not on certainty, but on wonder. Somewhere between the stars and the particles, between the slow pull of gravity and the flicker of quantum uncertainty, lies a riddle that has haunted physics for over a century. We've learned to describe the large and the small, the steady arcs of planets and the jittering dance of electrons. We've charted black holes and built machines to watch quarks collide. Yet, the bridge between these worlds remains broken. Gravity, the force that shapes galaxies and bends light itself, refuses to fit into the shimmering equations of quantum mechanics. And quantum mechanics, the strange, precise poetry of the microscopic sputters and collapses when confronted with the smooth curves of space-time. They are the two great languages of the universe, but they do not speak to each other. This silence sits at the heart of modern physics, and the effort to break it to build a theory of quantum gravity is not just a puzzle. It is a journey to the edge of what we know, and maybe to the very edge of what we can know. General relativity, Einstein's towering insight, showed us that gravity is not a force in the traditional sense. It is the warping of space-time itself. Massive objects curve the fabric of reality, and other objects follow those curves. It is elegant, smooth, and beautifully predictive. Drop a ball, fire a rocket, measure the path of a planet. It all unfolds along geodesics, the straightest possible lines in a bent world. Gravity is geometry. Quantum mechanics, on the other hand, is about probabilities, about fields and particles, superpositions and collapses. It doesn't describe objects as solid things moving through space, but as waves of potential, collapsing only when observed. Time in quantum theory ticks along as a fixed background, a stage upon which particles move and interact. But in general relativity, time is not fixed. It flows differently depending on where you are, how fast you're going, how much mass surrounds you. Time can stretch and slow, even stop entirely at the edge of a black hole. So if one theory treats time as absolute and the other treats it as relative, how can they both be true? The problem deepens as we look smaller and think bigger. Near the center of a black hole, where gravity is immense and space is compressed into a point, quantum effects cannot be ignored. Yet our current theories crash into each other at that boundary. The math breaks, the predictions go haywire. We get infinities, places where curvature becomes infinite, density becomes infinite, temperature becomes infinite. These are not just hard to imagine. They are signs that something is wrong. And it is not just black holes. At the beginning of the universe, during the Big Bang, everything was compressed into an unimaginably tiny point, a singularity governed by both quantum rules and gravitational ones. To understand that moment, we need a theory that can handle both, a quantum theory of gravity. Several paths have been proposed. String theory suggests that particles are not points, but tiny vibrating loops of string, whose modes of vibration give rise to mass and charge. It's a breathtaking idea, one that unifies all forces and particles in a single framework. And in string theory, gravity emerges naturally from the vibrations of a particular kind of string. But the theory requires extra dimensions, spaces curled up so small we can't detect them, and a vast landscape of possible universes. It is elegant, but also elusive. Loop quantum gravity takes a different approach. It starts not with strings, but with space itself. It suggests that space is made of discrete chunks, tiny loops woven together like a fabric. These loops are not embedded in space, they are space. And in this view, Time and space are not continuous, but granular. At the Planck scale, the very geometry of the universe becomes quantized. Curvature comes in steps, not flows. Time ticks in, bursts, not streams. Gravity, in this model, is not the bending of a smooth fabric, but the evolution of these loops. Other approaches explore even more radical territory: holographic principles, emergent spacetime, twistor theory, non-commutative geometry. Each offers glimpses of a deeper structure, a truth that might lie beneath the smooth veneer of reality we observe. But none have yet delivered the unifying insight that makes all the pieces fall into place. And perhaps this is the most humbling part. We may be close, or we may be centuries away. The edge of knowledge is not a straight line, it is a fog, a region of ideas and questions where clarity fades and the rules begin to blur. But what quantum gravity promises is not just a mathematical fix. It is a new way to think about what space and time actually are. If we succeed, we may discover that the universe is not built on particles and forces, but on information. That space is not the emptiness between things, but a cost of alongs, network of relationships. That time is not a river flowing forward, but a tapestry being stitched together from all directions at once. It may change how we think about birth and death, about cause and effect, about beginnings and endings. It may reveal that the universe itself is not a place, but a process. And when we finally find the bridge, when quantum mechanics and gravity shake hands, we may discover that they were never separate to begin with, that the division was in us, in our language, in our assumptions. Because the universe does not have to make sense in ways that are comfortable. It only has to be true. And the search for that truth, in all its strangeness and silence, is perhaps the most human thing of all. In the dim silence of laboratories, where lasers hum and detectors blink in quiet vigilance, some of the most unsettling truths about the universe have been revealed not through imagination, but through experiment. These aren't just thought puzzles or mathematical curiosities. They're real setups, real devices, real particles, behaving in ways that seem to violate everything we thought we knew about cause and effect, about space and time, about the nature of reality itself. Among them is an experiment that began with a question so bold it felt almost sacrilegious. Is the world truly made of definite things, or do possibilities only solidify when we look? In the 1,960 seconds, physicist John Bell devised a way to test whether quantum mechanics could be explained by hidden variables, some unseen properties tucked into particles, preserving the idea of a universe that behaves logically beneath the surface. If particles were secretly carrying instructions, then even the weirdest behaviors could be chalked up to ignorance, not magic. Bell's theorem outlined a set of conditions, inequalities, really that any theory based on hidden variables would have to obey. If those inequalities were ever violated in an experiment, then no hidden variable model, no matter how clever, could explain quantum behavior. When physicists ran the tests, starting with Elaine Aspect's famous experiments in the 1,980 seconds, they saw what Bell predicted. The universe violated the inequalities. Particles, when entangled, didn't just share information. They acted as if they were part of the same entity, even when separated by kilometers. Measuring one instantly influenced the outcome of the other, with no time for a signal to pass between them. Not a delay, not a suggestion. An immediate correlation, faster than light could ever travel. No message passed, no energy exchanged, yet something undeniably changed. It wasn't just a blow to classical physics, it was a blow to realism itself. Bell's theorem and its experimental confirmation forced us to abandon either the idea of locality, that distant events can't affect each other instantly, or the idea that physical properties exist independently of observation. You can't keep both. One has to go. And then came the quantum eraser, If the double-slit experiment already showed that particles can behave like waves, spreading through both slits until observed, the quantum eraser took it further, much further. In this version, particles, often photons, were sent through a double-slit apparatus, but with a twist. Detectors were set up to record which path each particle took. Unsurprisingly, when this which path information was known, the interference pattern disappeared. The photons acted like particles, not waves. But then, something unsettling happened. Physicists added a mechanism to erase the which path information after the photon had already passed through the slits, but before the final detection. When this erasure was performed, the interference pattern came back, not just as an average, but in individual detections sorted by coincidence. It's as though the particle retroactively decided whether it had gone through both slits or just one, based on something that happened later. Even stranger was the delayed choice quantum eraser. Here, the decision to erase or not erase which path information was made after the photon had already hit the screen. Somehow, the particle's past behavior, whether it had interfered with itself as a wave or traveled a single path as a particle, depended on a future event. It was as if time itself had become soft, responsive, subject to the act of observation. No signal traveled backward, no paradox emerged. But the implications were no less jarring. In a quantum world, what we call history is not fully written until the present makes its observation. The past, in some meaningful way, remains in superposition until we choose to resolve it. And then there are experiments with entanglement swapping, where two particles that have never interacted become entangled through intermediaries that themselves are entangled. Again, the choice to entangle or not can be made after the measurements on the individual particles have already taken place. And again, the outcomes retroactively conform to the new relationships, as if the universe updates itself when we shift our lens. None of this suggests the future is rewriting the past in the science fiction sense, but it does tell us that the classical picture of objects with definite properties moving through a fixed stage of space and time no longer holds at the deepest level. In these experiments, reality doesn't behave like a machine. It behaves like a story being co-written as it's read. Each of these tests, grounded in rigorous logic and technological precision, whispers the same secret. The universe is not passively out there, waiting to be observed. It is, in part, created in the act of observing. Choices matter not just for outcomes, but for the shape of what has happened. The story bends around the questions we dare to ask. And as we design new experiments, entangling more particles, probing larger systems, blurring the lines between the quantum and the classical, we're not just testing nature, we're asking it how much it's willing to reveal and what it's willing to change when we ask. It's easy to fall in love with mystery, especially the kind that seems to promise hidden power, secret knowledge, or some enchanted truth just beneath the surface of the ordinary. Quantum physics, with its strange riddles and poetic contradictions, has become something of a modern myth factory. It carries the scent of something mystical, entanglement, uncertainty, reality, shaped by observation, and in doing so, it's been draped in layers of meaning it never asked for. Popular culture has turned it into a shortcut for magic, a catch-all explanation for anything too strange to name. But behind the shimmering curtain of interpretation is a field more precise, more disciplined, and far more beautiful than its myths allow. There's a temptation to treat quantum mechanics like a philosophy, or worse, like a spiritual tool. Claims swirl that our thoughts can collapse wave functions, that consciousness controls reality, that by aligning crystals or repeating affirmations, we can quantumly manifest our desires into being. These ideas are compelling because they make us feel powerful. They promise that the deepest laws of the universe are not just knowable, but bendable. And perhaps most of all, They offer comfort that chaos is actually order in disguise, that uncertainty is a kind of invitation, and that we, tiny as we are, sit at the center of it all. But that's not what quantum mechanics says. At its core, quantum theory is not about bending reality to our will. It is about measuring what can be known and accepting what cannot. It tells us that the world, at its smallest scales, does not behave according to our intuitions. It dances not to the rhythm of desire, but to the strict and silent beat of probability. An electron does not appear where you want. It appears where the mathematics allows. A photon does not choose its path based on belief. It follows the rules encoded in its wave function, rules tested and confirmed through experiment, again and again, with extraordinary precision. The observer in quantum mechanics is not you, sitting in meditation. It is not a mind, nor a soul, nor a force of intention. The observer is a physical interaction, a detector, a photon bouncing off an atom, a device recording a spin. Observation in quantum mechanics means measurement, an event in which a quantum system becomes entangled with the macroscopic world in a way that can no longer be reversed. It is not awareness, it is physics. And while it's true that this interaction can collapse, a wave function reducing a cloud of possibilities to a single outcome, this does not mean thoughts shape reality. It means reality, when touched by other parts of reality, behaves according to quantum rules. If consciousness plays any role, it is because it emerges from physical systems, neurons, synapses, molecules that are themselves governed by those same rules. But there is no evidence and no need to invoke minds as mystical instruments in quantum collapse. Crystals, too, have become tangled in the mythology. They are beautiful, they refract light, grow in silence, and hold within them perfect symmetries carved by the earth itself. But they are not quantum batteries. They do not store intention or focus probability waves or interact with the fabric of the universe in ways that bypass physics. They are arrangements of atoms, their properties well understood, their structure measurable down to the angstrom. There is awe in them, yes, but not magic. And yet, the myths persist. Perhaps because quantum physics doesn't just challenge classical ideas, it challenges the boundary between knowledge and belief. When we say a particle is in many places at once, when we speak of entanglement and non-locality, it feels like we're talking about something more than science, something ancient or cosmic or divine. But this is the danger of metaphor stretched too far. In trying to grasp the ungraspable, we build bridges of meaning that collapse under scrutiny. Quantum mechanics doesn't need to be mystified. It is already astonishing. It allows particles to tunnel through barriers, entangle across space, fluctuate into and out of existence in the vacuum of empty space. It gave us lasers and semiconductors, MRI machines, and atomic clocks. It is the most precisely tested theory in the history of science, and it is not done revealing. The real magic of quantum physics isn't that it lets us bend the world. It's that it describes a world already bent beyond belief, a world where particles are fields and fields are probabilities, where certainty fades at the smallest scales, and where the very act of knowing reshapes what can be known. A world not controlled by thought, but by structure, by mathematics, by laws so strange and elegant they border on poetry. This doesn't mean we are powerless. It means that power looks different than we imagined. It lies not in wishful thinking, but in curiosity, not in the illusion of control, but in the pursuit of understanding. The experiments we build, the questions we ask, the humility we bring to what we discover, these are the true tools of transformation. And perhaps the deepest lesson quantum physics offers is not that the universe is yours to command, but that it is far stranger than you are, that your mind, for all its wonder, is one brief flicker in a sea of entanglements. That meaning is not granted by mystery, but earned through exploration. The quantum world is not mystical, it is real. And in many ways, that makes it even more mysterious. There is a quiet rhythm beneath everything, a trembling that does not stop, even in stillness. Atoms do not rest, space is never truly empty, and the world we live in, the one that feels solid beneath our feet, fixed in its routines, is stitched together from uncertainty, built on foundations that flicker in and out of clarity. This is the heart of the quantum world, not chaos, but nuance. Not nonsense, but a truth so fine it slips between the fingers of everyday logic. We often speak of the universe in grand terms, as if it were a machine ticking steadily towards some cosmic purpose. But zoom in far enough, and that neat machinery dissolves. Electrons do not orbit like planets. Light does not travel in perfect beams. Particles do not always know where they are, or even what they are. They spread out like whispers, interfere like overlapping songs, and collapse like stories being told only when someone leans in to listen. And yet, out of this haze, this shimmering cloud of probability, arises everything we know. The warmth of sunlight, the taste of salt, the flicker of a memory, the beat of a heart. The uncertainty isn't a flaw, it's the canvas. Quantum truth is not about answers that sit still. It is about relationships, shifting perspectives, delicate balances. A particle exists not in one place, but in many, until an interaction snaps the waveform into a single outcome. But that collapse doesn't kill the other possibilities. They linger, silent and invisible, like drafts of a poem never shared. Every moment, every decision, every glance contains multitudes. Some become real. Others drift away, unchosen, unrealized but not meaningless. We are taught to seek certainty, to pin things down, to declare them known. But quantum physics reminds us that knowledge has a texture, that beneath the facts we trust are layers of mystery. Not because we're ignorant, but because that's how the world breathes. Measurement gives us results, but those results don't reveal a single truth. They mark a boundary, a crossing, the end of possibility and the beginning of history. Somewhere in a lab, a photon chooses a path. Somewhere in your body, an electron tunnels through a barrier. Somewhere in deep space, a pair of particles entangled long ago still mirror one another's state. These aren't anomalies. They're how the world works when no one's looking. They're what happens when we stop pretending the universe is built for our intuition. And still, in all this strangeness, there is coherence. Not the tidy sort, but a larger one, a kind of music to the randomness, a symmetry to the contradictions, a structure that's more about probability than precision. The laws of quantum mechanics don't tell us what must happen. They offer a map of what could. They give us a field of options and let the world choose from within. You, too, exist in a kind of superposition, not of location or spin, but of becoming. Every second, you collapse into the present version of yourself, chosen from countless paths. You cannot rewind, cannot sample the others, but they're there, in the math of your story, in the skipped conversations, the almost decisions, the quiet shifts in the way you see. You live in the middle ground between particle and wave, between known and unknown, between being and becoming. And that's what makes it poetry, not because it's vague, but because it's precise in its ambiguity, because it holds tension instead of resolving it, because it invites wonder where others demand explanation. The equations work, but they don't silence the questions. They make them more beautiful. Why does entanglement exist? What is a wave function really? How can a choice made here influence something light years away without sending a signal? These aren't gaps in understanding. They are signposts. They remind us that science is not just a tool for control, it's a lens for awe. So here we are, drifting in this strange sea of probabilities, tethered to nothing but observation and time. Every moment you live is the outcome of countless chances, stitched together into a thread of experience. And still, the quantum world hums beneath it all. not demanding belief, but offering invitation to look closer, to wonder more deeply, to live not despite the uncertainty, but because of it. Because within that uncertainty is freedom. Within the blur is beauty. Within the trembling edge of what we know is a kind of truth that doesn't settle but sings.